We're going to be talking about some of the material, the optional readings that were in section 7.3 and 7.4. Today we talked about some of those optional readings, particularly decision tree induction on Tuesday as well. So here's the general setup for supervised machine learning. And again, there are lots of forms for machine learning, lots of different types of machine learning. And in this chapter, the book talks about those various forms, those many various forms, and talks about where in the book you can find discussion of those various forms. It's not in one chapter, it's actually in 4 chapters because of the variety of machine learning techniques. But we're going to be talking about, and we have talked about Tuesday, one of the most popular forms, supervised machine learning. And the goal of supervised machine learning is to take data, which is labeled, this is known as training data, and to learn a classifier, to learn an association between a set of, or vector of independent features or attribute values and classes. So after learning that association, or those associations, presumably, and you build a classifier that encodes those associations, you can give your classifier, provide your classifier with an unclassified example, just a vector of independent features, and it will predict what the classification, what it expects the classification should be. And as with most things, for any non-trivial learning task and prediction task, it's rare to get 100% prediction. And so what we hope for is we hope to get very high accuracy, or in this case, on the last lecture I demonstrated both high accuracy output, which would be a curve like this, as well as what is also common, particularly in the book, to measure error rate, in which we would expect error rate to decrease with increased learning, or in some cases response time. We would expect response time to decrease with increased learning on some task. What we're going to be looking at in particular are learning methods that build classifiers. And classifiers are, data structures or knowledge structures for predicting outcomes, but the outcomes are qualitative. That is, we are predicting a soybean plant has a sick euthyroid, or sick one kind of disease or another. Or if we're talking about thyroid patients and predicting thyroid illness, one of the classes might be sick euthyroid, one of the classes may be no disease at all, another class may be hypothyroid. But these are qualitative predictions. And when the predictor is making predictions exclusively about qualitative attributes, we call it a classifier. A predictor is more general, that includes both qualitative predictions and quantitative predictions. So if our machine learning system is actually a regression system, and the book talks something about those, linear regression, for example, as making a prediction along a continuous dimension, then we would call it more generally a predictor. But we're going to be concentrating on classifiers, and have been since Tuesday. So just to remind you, in supervised learning, and I qualify this further by data-driven supervised learning, there are other forms of knowledge-intensive learning where you have a lot of knowledge about a domain ahead of time. We have a set of classified examples. This is a training data set. We want to find a classifier for predicting class membership of unclassified data. And we're going to use a test set for that. That is data like this, but without a known classification. And we make a prediction about the classification, and then we compare it against its correct classification, which was hidden prior to testing. I make a few weak assumptions here about using binary classes and binary variables, but really not strong assumptions here about those. So we talked about decision tree induction on Tuesday, went into some depth about it. And today I'm going to introduce you to another form of supervised machine learning. In general, this is known as a Bayesian classifier. We have a vector like this with the independent features and an unknown value for the class. In the Bayesian classifier, we're going to compute two probabilities if we have two classes. If we have more than two classes, we're going to compute a probability for each of the possible class outcomes. But that probability is basically going to be, we're going to be computing the conditional probability of class 1 in this example, given this vector. What's the probability of class 1 given these attributes? And we can rewrite that as a joint probability over all the features plus the class divided by the probability of the conditioning information alone without the class. And we are also going to compute the probability of the other class or any other classes, C2 in this example, which will have a very like form here, compute the conditional probability of C2 given the same vector, which again we can represent as a fraction over the entire vector, including the class filled in as C2 divided by the conditioning information, the joint probability of the conditioning information alone. And what we want to do in the Bayesian classifier is we would classify this vector as C1 or C2, whichever has the higher conditional probability. So it's nice and intuitive. If you've not looked at probability, I suggested that you read 8.1 if you don't have a background in probability, and you don't even have to go through the entire 8.1 section to, I think, get a handle on probability. But we're not going to cover what I regard as background material too much in lecture. I'll give examples here and there, but I'm expecting you to go back and look at that, or see me or Brian, one of our TAs during office hours if you need an additional help. And we can make a special appointment. If this is something that, if probability is not something you've had in, it's not taught every year in 212, you may not have had it, it's not a formal prerequisite of this course, then you probably want to come in and see me. But the basics that are required, I think, are pretty minimal. But just some background that you would concentrate on looking at the book. Conditional probability is, again, just represented as a joint probability over both these factors divided by the probability of the conditioning information alone. Here's an example with particular values. The probability of A given B is equal to the probability of A and B divided by the probability of B. Notice that a vector like this contains both A and B is more restrictive than the requirement that the vector simply contain B. And so this is the probability within, say, the training set that a vector, arbitrary vector, contains both A and B. And because that's more restrictive, we know that this probability is never going to be greater than this probability, because the constraints on this are greater than the constraints on this. So it's possible they're the same, but typically they'll be less than. So the idea here is the probability of A and B in the set of training vectors as a whole might be 0.5, but the probability of B all by itself is 0.75. So if I know that a vector contains B, then 67% of the time it's also going to contain A. But again, go back and look at that background as you need to. So let's continue with the Bayesian classifier. In this case, this is the conditional probabilities that we were just talking about. And this is the exact, if I include that crossed out denominator, this is the exact value for that conditional probability. But notice in this case, in the case of the Bayesian classifier, we're just making a relative judgment. All we want to know is which has the higher probability. In many cases, we don't need to know the exact probability. We just want to know which of the options, C1 or C2, or C3 and C4, if there are some, has the higher probability. And to do that, we just need to focus on the numerators, because the denominators in these cases are going to be the same. And so, for a particular example, this conditional probability is proportional to that joint probability. And all we're really going to compute is these two joint probabilities and select the one which is larger. If we do want to accompany that prediction with an exact probability in each case, and we might want to do that in a lot of cases, we would compute the exact probability. But just for comparative purposes, we're just going to look at those joint probabilities. Here's some more background, and again, take a look at it to some extent offline. I'll just review briefly what it says, though. It's called the chain rule. So we were just talking about comparing joint probabilities. And I'm introducing this background as a guide for you to focus on just that stuff from the 8.1 chapter that you really need to understand the naive Bayesian classifier. But here is a joint probability, including the class and some conditioning features. We can factor that into a number of conditional probabilities. So this joint probability equals the probability of the class value times the probability of V1 conditioned on the class value times the probability of V2 conditioned on the class value and the V1 value. And you can take a look at the rest, that the conditioning information grows on these subsequent variables. And in this case, I've used a factorization ordering that follows the order of these variables here. If I multiply these two values, what I get is the joint probability of C and V1. The probability of C by itself times the probability of V1 given C is going to be the probability of C and V1. And if you go back to the earlier slide and look at that example I gave you on the definition of a conditional probability, you'll see that. I multiply this times, this corresponds to the conditioning information here. This gives the joint probability of these three values. And I continue and I get back the conditioning information on all values, or the joint probability on all values. Importantly, although not terribly importantly for us right now, is we can select any ordering of these. And so we can start with the probability of V4 times the probability of V2 given V4. And this factorization ordering will give us exactly the same result as this factorization ordering. Any factorization ordering will give us the same result. For convenience, though, we'll typically use this one where the unconditional probability of the class is by itself. The last piece of background we really have to understand what is called the naive Bayesian classifier, which is a very simple learning method, a very simple classifier, but nonetheless does pretty well, is the notion of conditional independence. And in conditional independence, here is the joint probability. Here is the exact definition or the exact value of the joint probability. This equality is always true. This will always equal this, and for that matter, as I just said, any other factorization ordering. But if the VIs are independent, conditioned on the class, sometimes said the conditionally independent given to the class, then we can rewrite this as this. Notice that in this case, these two values are the same, but if the V sub i's don't depend on one another, if you know the class, then we can rewrite this value as this one, excluding additional conditioning on V1. That is, if I know something is a member of a class, knowing its V1 value gives me no additional information in predicting its V2 value. Likewise, the conditional probability of V3 given C and other conditioning values is simply equal to the probability of V3 given the class. So this equality is only true if we have this property of conditional independence, and more often if we assume the property of conditional independence. It may be very rare for conditional independence to be achieved in a pure sense, but very often it's convenient just to assume it. And here's a couple of examples of where we might have conditional independence, or even if we don't have perfect conditional independence, where we might assume it nonetheless. So in one particular example, we might be looking at classes of animals, mammals, bird, and fish. And these classes have fairly features, a number of features which are virtually, in some cases, definitional of the class, in other cases, almost definitional of the class. And if I take a look at, say, what is the probability of a mammal having hair and a four-chambered heart and walking? It's close to 1. It is close to 1. And so the probability of this joint probability is very close to the probability of mammal times the probability that the mammal has hair times the probability that it's four-chambered heart times the probability that it walks.